This is the next presentation in my series on the universe. It deals with what happens when electrons are added to nuclei to form atoms. It requires knowledge of the Rutherford model of atoms, in which a small, dense, positively charged nucleus is surrounded by electrons. It also requires knowledge of the structure and properties of electrons under this rotating photon model, as given in some previous presentations. It doesn't require knowledge of quantum mechanics, apart from Planck's constant. Instead, I show that the proposed quantum mechanical ideas are just the natural consequences of treating electrons as particles under this model. In previous presentations, I've shown the properties that are common to all particles that are composed of rotating photons of the appropriate energy, making 2 revolutions per wavelength. That was followed by an introduction to subnuclear particle physics and nuclear binding to form nuclei. It is now time to show what happens when electrons gather around nuclei to form atoms. It explains the electron properties that enables them to bind to form all materials we have around us. That gives us our stable base here on Earth from which we can observe the rest of the universe. The properties of electrons in atoms and their ability to bind atoms together in molecules, crystals, metals, solids, liquids, and gases have been studied extensively over the past 120 plus years since Thomson's discovery of their particle nature. Early researchers developed concepts such as Rutherford's planetary model of the atom, Pauli's exclusion principles, Bohr's quantized electron orbits around the nucleus, de Broglie's particles having a wavelength, and the use of waved electrons to solve electron properties such as those of Schrödinger and Dirac. These appear to work quite well, so why bother with a different interpretation? The answer is found in both the extensive use of wave properties and equations to calculate effects when electrons are particles, and the number of postulates required to make them work. In this presentation, I intend to show that by treating electrons as particles under this rotating photon model, a number of postulates are automatic consequences of their structure and properties. There is no need to introduce concepts like quantized orbits or the exclusion principles. Further, their particles give a better description of electron behavior in atoms than does treating them as waves. Finally, when researchers know what is physically happening, they may be in a better position to predict other properties. The simplest atom to discuss is the hydrogen atom. It has 1 proton in the nucleus and 1 electron associated with it to form a neutral atom. The standard model treats electrons as point particles with a dimension of less than 10 to the minus 17 meters. Rutherford's planetary model suggested that electrons orbit the nucleus like planets around the sun. That model had 2 problems. In order for a charged particle to change its direction, it has to emit photons. Emitting photons means that it would lose energy and spiral into the nucleus, as illustrated in diagram A. That would cause the atom to collapse. It doesn't happen. To explain why, Bohr modified the model to indicate that electrons could travel in fixed or quantized orbits, as indicated in diagram B. The orbits were quantized in terms of the electron's orbital angular momentum at that radius. It was sometimes considered as integers of the de Broglie wavelength. That offered a number of advantages. It meant that electrons didn't have to emit photons to travel in those confined orbits. The orbits didn't include the nucleus, so they wouldn't collapse into it. Electrons would only have to emit or absorb photons as they changed orbits. It was a successful theory that is still widely used. Rydberg derived an expression for the binding energy of a single electron to a single proton. It was given by Re equals me E squared over 8 epsilon naught squared H squared, and it was 13.606 electron volts. It matched experiment very well. It meant that it required an energy of 13.606 eV for a photon to eject an electron from a hydrogen atom. An electron captured by an isolated proton or a hydrogen nucleus emits a photon of energy at least 13.606 eV. Bohr's quantization of angular momentum indicated that there are stable orbits at other integer multiplications of the angular momentum wavelength. That gave rise to different series of spectra as electrons can transit between different levels. They are the Lyman, Balmer, Paschen, and Brackett series as electrons transition to or from n equals 1, 2, 3, and 4 times the quantized angular momentum wavelength respectively. They have been observed. Altogether, that equated to a successful outcome from treating electrons as quantum waves. Now it is time to see what happens when we treat electrons as particles under this rotating photon model. The first thing to note is the size difference between a proton and an electron. Protons have a root mean square charge radius of 0.87 by 10 to the minus 15 meters, herein referred to femtometers or just FM. That little red dot just near the upper corner of P in proton represents a proton with a radius of 1 FM. An electron at rest has a radius of 1.93 times 10 to the minus 13 meters, or 193 FM at rest. That radius doesn't change with energy of 13.6 eV. The blue circle around it represents the rotational axis of an electron of rest radius 193 FM drawn on the same scale. It does not represent a point particle traveling around at that radius. The blue circle represents the central axis of the rotating photon that is the electron. The electron is very big compared to a proton. Under this rotating photon model of matter, the more massive is a particle, the smaller it is. So even if the classical Rutherford model applied, which it does, and the electrons emitted energy and spiraled into the proton, it would not fit. So there is no need to introduce any quantized orbit concept to prevent an electron spiraling into the nucleus. It physically won't fit. And not only that, even if you could get an electron into a hydrogen nucleus, there are no energy levels available to absorb it. Tritium, 3H, decays by emitting an electron, not capturing one. It is time to re-evaluate the Rutherford planetary model in terms of this model of an electron. The first feature to note is that for its mass, the electron is one very powerful gyroscope. Its whole mass is rotating at the speed of light at a radius hundreds of times larger than the much more massive proton. It can't change direction unless it has a partner with which to exchange angular momentum. That can only be done through photon exchange. An electron caught in the potential well of a proton will move back and forth and over and or around the proton, changing directions only when it receives a photon from the proton. The potential well within which it is captured has a single value, as determined by Rydberg's energy of 13.606 electron volts. I'll now move on to electrons around larger nuclei. The first feature to note, as shown in this diagram, is that even a large uranium nucleus, including the skin effect, has a diameter of about 1/20th of that of an electron. An electron can't physically fit into the largest nucleus. There is no need to ever consider the possibility of quantized orbits being needed to prevent electrons from being captured by the nucleus. The electron's axis of rotation is vastly larger than even the largest nucleus. From now on, I'm going to talk in terms of the ionization energy, IE. It is the energy required to remove an electron from the potential well in which it has been captured by the nucleus. For a single electron around a nucleus containing Z protons, that is given by IE of Z equals RE times Z squared. That equation is well known and its derivation is independent of the model of the electron. There is no need to derive it again. The important feature is that the ionization energy sets the boundary conditions of the captured particle. That is no different from a satellite orbiting a planet. The potential energy at which it is captured sets the boundary conditions of distance from the planet or star at which the speed of the planet orbits. That is where the similarity ends. Electrons interact with each other and also screen out the attraction of one proton from the nucleus from the other electrons. It is now time to see what effect that has. The next simplest atom is helium. 2 electrons attached to a nucleus containing 2 protons. The equation for IEZ binding energy for a single electron places it in a potential well of 4 times the Rydberg energy, namely 54.42 electron volts. That calculation has been determined by others and is fixed for 1 electron in any model with the same mass and charge. The first electron is referred to as the 1s1 electron. It screens out part of the charge from the nucleus. The second electron, the 1s2 electron, will have a lesser ionization energy. The bottom equation suggests that it is screened as a function of the binding energy of the 1s1 electron. That function will be discussed later, i.e. 1s2, the binding energy of a 1s2 electron, has been measured at 24.59 electron volts. This gives a not-to-scale representation of a helium atom. At its center is the nucleus. It has a root mean square charge diameter of about 3.4 FM. It has 2 electrons moving around it to neutralize its positive charge. Their movement is constrained by the potential well created by the 2 protons inside the nucleus. They move back and forth within the constraints of that potential well, passing all around the nucleus, screening out its positive charge. They have maximum kinetic energy near the nucleus and travel out until constrained by the potential well. Note that the helium atom is drawn without a clearly defined boundary. The electrons move back and forth around it and about the nucleus, with their probability of being located diminishing with their distance from the center. It's a diffuse boundary beyond which they will not be found. As mentioned earlier, an electron can't change its direction of travel unless it emits or absorbs a photon. Their proposal went with the Rutherford model. If it has another particle with which it can exchange angular momentum through photon exchange, it can change its direction without losing energy. 2 electrons around a 2-proton nucleus create a unique situation. By exchanging photons, the pair can move in any way determined by their circumstances. They have no need for another electron with which to exchange photons and hence angular momentum. It is that exchange of photons between 2 electrons that enables them to move around the nucleus while staying in the potential well created by that nucleus. That is what makes helium an inert atom. The 2 electrons are screening out all the positive charge of the 2 protons. The nucleus can't attract any more electrons. They are more strongly attached to the nucleus than any other outer orbit electrons. That also makes helium atom the smallest chemically inert atom. A single hydrogen atom is smaller. It has a single electron and no other electron with which to exchange angular momentum. It will find another electron with which to associate. If that is with another hydrogen atom, the molecule that it formed is far larger than the helium atom. From there, the electrons move back and forth under electric attraction from the nucleus. During their passage, they will exchange photons, changing their trajectories, and will travel in different directions. They will both have the same average energy, approximately 40 eV, giving them an average maximum speed of about 4 times 10 to the 6 meters per second. They have that speed when they are close to the nucleus. As they move to the boundary of the potential well, they lose kinetic energy as they gain potential energy from the nucleus. That will give them an average speed of about 2 times 10 to the 6 meters per second. In a potential well diameter of about 0.1 nanometer, each electron would transit the potential well boundaries about 2 times 10 to the 16 times per second. with a change of direction possible in each transit. That gives plenty of opportunity for each electron to circumtransit the nucleus in all directions, screening out all the nucleus's positive charge. The Bohr radius is determined from the same potential well. In the Bohr model, the electrons travel around the nucleus like planets around stars. Each electron's wave function is treated like a probability function, with the electron's most probable location being either side of the Bohr's radius, somewhat as illustrated in the left-hand side diagram. In it, the electrons are physically distributed around the circumference of the Bohr radius. There is some similarity between the Bohr model of quantized orbits and this rotating photon model. Both rely on the potential well of the captured electron. The Bohr model relies upon quantized orbits to prevent the electron from collapsing into the nucleus. It also relies on the electron's wave function probability to distribute the electrons in a diffuse torus or donut shape around the nucleus, followed by a not often stated reason for the torus to rotate around the nucleus to enable the electron to screen out the proton's positive charge. In this rotating photon model, the electrons are also constrained within the nucleus's potential well. That makes the energies of the two models the same. From then on, the electrons move back and forth within the potential well, exchanging photons and changing their direction of travel as they completely surround the nucleus with their charge. They don't need any quantization to prevent them from sliding into the nucleus because they are simply too large to fit into any nucleus. Their trajectories take them beyond the Bohr radius with an ever-decreasing probability that it reaches zero at or near the boundaries of the potential well. The postulate about the spin of two electrons in the same orbital being opposite was introduced to prevent two fermions occupying the same place in space-time. There is no need for that postulate. The electrons, like electric charge, will keep them from occupying the same point in space at the same time. As it is, quantum mechanics specialists don't know what spin is. They often quote the Stern-Gerlach experiment as being an indication of measuring spin. The reality of that experiment is that they are measuring the magnetic field of the single unbound electron and relating that to the property they call spin. The Stern-Gerlach experiment does not measure spin as such. After all, both stable nuclei, isotopes 107 and 109, have equal numbers of neutrons with one unpaired proton. That gives silver nuclei a spin of half h-bar, the same as that of the unpaired electron. If the experiment was indeed measuring a single atom's spin, each atom could have one of three possible spin values: -1 when the two are aligned in the same spin down direction, 0 when they are aligned in opposite directions, and +1 when they are aligned in the spin up direction. So don't be too impressed when quantum mechanics specialists start talking about spin. They don't have a clue what it is. They measure the direction of an electron's magnetic moment and assume it is related to its spin. That was possibly due to the work of Uhlenbeck and Goldschmidt a couple of years earlier. They explained the splitting of the spectral lines from atoms in a magnetic field as being due to the electrons having an internal angular momentum. That, of course, is what it has under this rotating photon model of the structure of particles. In all probability, paired electrons would orient their magnetic fields in the same direction to minimize their energy. Moving back and forth over 10 to the 15 times per second makes it difficult to measure the magnetic moment of individual electrons. The average will always be 0. That leaves a valid assumption that they must have opposite spins seem quite valid. I repeat my earlier comment. The postulate about two electrons in the same orbit having opposite spin is an unnecessary mathematical sleight of hand to cover up that they don't know what is happening inside the electron's wave function. This rotating photon model relies upon the potential well generated by the protons in the nucleus. That is determined by the number of protons in the nucleus. It is that which sets the energy levels available to electrons. After that, no other rules are required. The electrons will move within the potential well, with each electron screening out the positive charge of one proton from the other electrons as they completely surround the positive nucleus. The helium atom presents a closed system to other particles. It has no need to attract another electron to help either neutralize the nucleus's positive charge or to provide the photons for the electrons to exchange angular momentum and move in different directions. It is a completely inert entity. It is now time to have a look at the general situation involving the first two electrons around a nucleus with Z protons. Others have already calculated the general formula for a single electron, denoted 1s1 around a nucleus. It is given by the top equation. It shows that the binding energy for a single electron to a nucleus containing Z protons is Rydberg's energy multiplied by Z squared. A general expression for the binding energy of the second electron, denoted 1s2 for an electron around a nucleus containing Z protons, is given in the second equation. The IEZ1s2 term is just the 1s1 ionization energy screened by the 1s1 electron. I am sure others have derived similar expression, although I haven't bothered spending time to look for them. I just found it quicker to derive my own. This table shows the calculated and measured in bold values for the ionization energies of 1s1 and 1s2 electrons around nuclei with Z from 1 to 24. One important feature here is that the ionization energy for each 1s1 electron is fixed by the number of protons in each nucleus. That for the 1s2 electron is set by the screening effect of the 1s1 electron upon the charge of one proton in the nucleus. The agreement of calculated values with measured values is very reasonable. The differences are never more than about 3 electron volts or about 0.75%, whichever is the larger. Both equations could do with a slight modification, but it won't affect the overall concept that the binding energies of electrons are fixed by the potential well of the number of protons in the nucleus and the screening effect of the other electrons around the nucleus. This table suggests there is no need to introduce fixed energy quantized orbits to explain electron ionization energies. They are fixed by the number of protons in the nucleus and the screening effect of each electron has on one proton in the nucleus. We can now apply the same screening principle to other higher number electrons. The top equation suggests the binding energy for a 2s1 electron around a nucleus containing Z protons is a function of the binding energy of a nucleus with Z minus 2 protons. That includes the allowance for the two inner 1s electrons to push the other electrons out. In a similar manner to the previous 1s2 equation, an equation for the ionization energy of a 2s1 electron is given by IEZ of 2s1 equals 0.25 ReZ squared times Z minus 2 squared plus 0.2 Z minus 2. The 2s1 electron is the first electron in the second energy level after the two 1s electrons have screened out the effect of the two protons inside the nucleus. The two inner electrons have forced the next set of electrons further away from the nucleus, reducing the intensity of the ReZ squared effect available for the first 2s1 electron. That process can be continued as required until all energy levels are covered. Now, this is chemistry. I'm sure chemists have worked that out before. I just want to extend the screening principle to the energy levels of 2s2, 2p1 and 2p2 energy levels. They are given by these equations, i.e. Z2s2 equals i.e. Z2s1 minus Re times 0.6 plus 0.3 Z minus 3. The IEZ2P1 equals IEZ2S2 minus RE times 0.5 plus 0.5 Z minus 4. And the IEZ2P2 equals IEZ2P1 minus RE times 1 plus 0.33 Z minus 5. In these equations, the electrons are screening out some of the charge left after the 2s1 electron has screened out some of the charge. That is why each of these equations is based on the ionization energy of the previous electron, with a term that subtracts the additional screening effect of that electron. This slide shows the results of calculations for 2s1, 2s2, 2p1, and 2p2 electron ionization energy levels for atomic numbers up to chromium, Z equals 24. There is no need to study it in any great detail. Scan the theoretically calculated columns and then the experimentally measured columns in the bold to their right. They will show that the experimentally predicted values are within a few electron volts or less than about 1%, whichever is larger, of the experimentally measured values. These calculations are used to show that simple screening calculations match the observed ionization energies of electron energy levels and a range of atomic numbers. Those energy levels are determined by the potential wells associated with the number of protons in the nucleus. They are discrete values that naturally exist without the need to introduce a special requirement like limiting electron orbits to quantized angular momentum or fixed numbers of de Broglie wavelength. Have a look at these predicted and measured values. I admit the calculations are a bit wobbly at lower Z values, with some differing by a few percent. It is different at the higher Z. Look at the Z equals 10 row. Predicted 306, measured 300. Predicted 208, measured 207. Predicted 160, measured 158. Predicted 129, measured 126. Or the Z equals 24 row. Predicted 1720, measured 1721. Predicted 1634, measured 1634. Predicted 1491, measured 1496. Predicted 1392, measured 1396. These differences are well under 1%. They give the strongest possible indication that the energy levels available for each electron is due to the screening effect of inner electrons over the protons in the nucleus. So I repeat, there is no need to introduce quantization due to orbital angular momentum or the de Broglie wavelength. Electron energies are fixed by the number of protons in a nucleus and the number of inner electrons that screen out the charge of some of those protons. The relative success of the Bohr model of electrons orbiting the nuclei in quantized orbits appears to have put the blinkers over people's eyes to other possibilities. A nucleus is not like a sun. With about 10 to the 57 nucleons in the sun, it can provide a continuum of energy and orbit levels. Nuclei have only a fixed and integer number of protons within them to attract electrons. Electrons aren't artificially constrained by having to travel in quantized orbits. Individual electron energy levels are fixed by the limited number of protons in a nucleus and the screening of inner electrons on the nucleus's positive charge. These fixed ionization energy levels can be called quantized. Under the Bohr model, this quantization is due to angular momentum. It is your choice as to which you prefer to believe. Those who doubt this interpretation should try to calculate those wavelengths using either integer number of de Broglie wavelength or quantized orbital spins. I think you'll find the agreement is not as good as is given in this table. The reality is electrons don't limit themselves to orbiting the nucleus like planets. Such an action would not give any opportunity for them to surround the nucleus in the third dimension without postulating yet another law. In 1989, when commenting on the Bohr model, Berry observed that two atomic electrons kept in the deep potential well close to the nucleus, but in the same neighboring shells, behave for the most part like a collective molecular-like system more than they behave like quantum mechanical analogues of the solar system. Energies, and in applicable cases, angular momenta, are approximate constants for the collective mode of vibration and rotation, better approximate constants in most cases than the energies and angular momenta we would attribute to individual electrons in the orbitals appropriate to an independent particle model. Those comments of two atomic electrons behave for the most part like a collective molecular-like system are what would be expected under this rotating photon model for the structure of electrons. The reason is simple. Mass for mass, electrons are the universe's second most powerful gyroscope. They can't change their direction of travel unless they have another electron with which to exchange angular momentum. Then they can move freely as dictated by the potential well produced by the positively charged nucleus. With all the photons being emitted and absorbed by charged particles, it is easy for one electron to associate with another electron and the two to move as determined by other circumstances. That forms the basis of Berry's second comment, that collective angular momenta more reflect observation than the individual angular momentum proposed by Bohr. There is no need to introduce quantized orbit terms. Electron energies are fixed by the potential well of the number of protons in the nucleus and the screening effect of inner electrons on the outer electrons. I have mentioned electron pairing to exchange photons. That can also occur between groups of paired electrons, as observed by Berry. It can't occur with an unpaired electron. It is that which causes an unpaired electron in an atom to seek another unpaired electron with which to pair. That forms the basis of chemical bonding. It is now time to have a look at some examples of how electrons bind atoms together. This slide shows what happens when two electrons come close together. The gray intensity suggests the most probable distribution of the electrons. Each electron is represented by blue and is traveling around a nucleus represented by red. Diagram A shows two isolated hydrogen atoms. The electrons can move about the nucleus by exchanging photons with the nucleus. I mean, it can occur, but with a huge mass difference, it makes it difficult. B shows when two atoms are close enough together, the electrons will exchange photons, allowing them to move more freely together. Their need to exchange photons to move more freely as a pair brings them together to form a molecule, as shown in C. The dimensions and properties of the molecules are determined by the proton's mutual repulsion being screened by the electrons, along with the electrons' mutual repulsion being tempered by the need to be close to and exchange angular momentum to move around the pair of nuclei. Now it is time to look at what happens when two helium atoms approach each other. D shows that both electrons can move freely because they already have each other with which to exchange photons and hence change direction of their angular momentum. Move the two together as shown in E, and the electrons in each atom will repel those in the other atom. Helium is an inert atom because its pair of electrons has all that is required to move freely around the nucleus, and they screen out all of its charge from all other electrons. This reminder of the Rutherford atomic model in F is brought back to indicate that Rutherford was correct in some ways. An electron needs to emit or receive a photon to change its direction. It doesn't do it in empty space. It does it by exchanging photons with another particle, which is almost always another electron. Together they can move, including in an orbital motion, without having to spiral into the nucleus as they lose energy. I mean, even if they did, they would be far too big to fit into any nucleus. Now it is time to show just a little about how the rotating photon structure of electrons automatically leads to some known chemistry properties. The simplest example is adding a hydrogen atom to a lithium atom. Both have one electron that does not have another electron with which it can exchange angular momentum through photon exchange. When they are close together, the two single electrons will exchange photons. Together they will be free to move around and between both nuclei. Because the two electrons share their time between both nuclei, they won't be able to go far from the Li nucleus as could a single electron. In that way, the addition of the lighter hydrogen atom means that lithium hydride molecule is smaller than the lithium atom. That is why lithium hydride is denser than lithium. And that is a covalent bond where both nuclei share the same pair of electrons. Fluorine is another element with a single electron that does not have a partner with which to exchange angular momentum. The nucleus marked S has two inner electrons designated 1s happily exchanging photons and otherwise unbothered by what happens outside them. Outside them, there are 7 electrons, 6 of which have a partner with which to exchange angular momentum through photons, and they will move freely within that potential well. The 7th does not. When a fluorine atom is approached by a lithium atom, the two single electrons will exchange angular momentum and become a pair. The low binding energy of a 2s1 electron to a lithium nucleus of about 5.4 eV versus the high binding energy for a fluorine atom, about 17.4 eV, results in the fluorine atom capturing the lithium atom's 2s1 electron. That gives it 4 pairs of electrons moving stably in the second potential well. The fluorine atom becomes a F- fluoride ion, and the lithium atom becomes an Li+ lithium ion. The two are held together by electric attraction of opposite charges. Note that the addition of hydrogen to lithium made lithium hydride denser than lithium because it gets rid of the large orbit of the lithium's weakly bound outer electron. Another example is fluorine capturing lithium's 2s1 electron. It leaves the lithium ion with its central core that is smaller than a helium atom. When that is attracted to the fluoride ion, the assembly is very small. That helps explain why lithium fluoride has a much higher density than lithium hydride and even fluoride liquid. At its boiling point, fluorine's density is about 1.55 grams per cc. You'll see that of lithium fluoride is somewhat higher. Another form of material bonding is metallic bonding. In it, electrons in atoms with low number of outer potential well electrons with low ionization energies can move relatively freely between all the ions. In this metallic bond illustration, the two S1 electrons have been removed. That leaves the positive lithium ion surrounded by electrons moving freely within them. The blue ellipses show the electrons. The black wave functions associated with them represent photons they may need to exchange to alter their direction. These moving electrons create a sea of negative charge, shown as pale blue, in which the positive lithium ions virtually float. The positive charge of the ions repel each other. They are prevented from moving away by the sea of electrons moving between them. The electrons can move without much hindrance because they have all given up their outer potential well electrons. That opens up a large pathway for them to move, making them electrical conductors. Atoms with large numbers of outer shell electrons can't do that. They are electrical insulators. Some of those with their outer electron shells half full are, would you believe, semiconductors. I am now well into the field of chemistry. The whole point of that lithium exercise was to show that this rotating photon model of electrons automatically leads to many of the postulates used in quantum mechanics. And those postulates have been successful in advances made in chemistry and other branches of material and biological science. I mean, those sciences cover such a vast array of topics that it's not possible to cover any in great detail. to various degrees. They are all based on what has been called the quantized properties of electrons in atoms. In this presentation so far, I've pointed out there is no need to introduce concepts of quantization. All electron energy levels are fixed by the limited number of protons in the nucleus and the screening effect of the inner electrons on protons within the nucleus. And when you take into account on top of that, the electrons can't spiral into a nucleus because they are far too big to fit into it. Those properties which are used in quantum mechanics are simply the natural consequences of the properties under this rotating photon model of particles. It's not quite as simple as that suggests. That would mean that every even Z atom was inert, and they aren't. However, there is a chemical trend that odd Z atoms are more chemically reactive than their nearest neighbor, even Z nuclei. Illustration A shows that aluminium and phosphorus, both of which have one spare electron, are more chemically reactive than silicon, which has all electrons paired. Chemists should have worked out why neon, Z equals 10, and argon, Z equals 18, are inert gases. The above has shown that two pairs of paired electrons in the outer shell of carbon made it less reactive than single pair even Z atoms either side of them. The same applies for silicon. For example, consider beryllium and oxygen either side of carbon. They are more reactive than carbon. In the same way, magnesium and sulfur either side of silicon are more reactive than silicon. Those atoms with one or three sets of paired electrons are more reactive than those with two sets of paired electrons. It is suggested that is because paired electron pairs make it easier to exchange angular momentum than a single pair, giving electrons in those atoms a lower trend to seek further electrons. In the same manner, four paired electron pairs makes exchanging angular momentum through photons so complete that there is no need to seek additional electrons from other atoms for the electrons to move freely around the nucleus. Although electrons need to be paired, they have no need to be monogamous. As mentioned in my first presentation, electric charge is caused by the continual emission and absorption of photons as the primary photon rotates. Electrons accept photons from any source that suits the circumstances. In covalent and ionic bonding, electrons accept photons from within their energy level group. But there are other forces where electrons accept photons from other sources. In van der Waals force, dipole moments in the molecules can interact with dipole moments in other molecules, causing them to bind together. That also occurs through photon exchange. By this stage, we are totally within the realms of chemistry and chemical bonding. And we reached it without having to introduce a single quantum mechanical property. Electron ionization energies, usually referred to as orbital energies, are fixed by the potential well of the number of protons in the nucleus, minus the screening effect of inner electrons. They do not have any special need to stop them from falling into the nucleus. They are simply too large to fit. Electrons are free to move around a nucleus, screening out its positive charge when they have a partner with which they can exchange photons. This model predicts, and Berry has observed, that electrons travel in pairs. That is a necessity because of the electron's very high angular momentum to mass. Angular momentum half h bar represents the whole mass of the electron traveling at the speed of light in a circle of radius 193 fm. They need to travel in pairs to exchange angular momentum, and photons is the way they do it. That is how they change their direction of travel. Nothing in this prevents electrons from orbiting or otherwise tracing fixed paths in pairs. Compare those with Bohr's quantized orbit model. He introduced quantization to overcome what he saw as classical deficiencies. In quantized orbits, Electrons don't have to emit photons, and they won't spiral into the nucleus. The electron's orbit was otherwise planar, like a planet. An additional postulate was required to make the electron's orbit rotate uniformly around the nucleus. The Bohr model has no explanation for Berry's observation. They just ignore it. Electrons are powerful gyroscopes that need to exchange angular momentum to change their direction of travel. They do that by exchanging photons with another electron or multiple electrons that are part of a paired group. In that way, they don't lose energy when changing direction. Their movements are typically 10 to the 15 oscillations per second as they move around the nucleus. Electrons travel in pairs because of their need to exchange photons so they can move in different directions. Because of their like charges, paired electrons can't occupy the same point in space-time. Now that occurs naturally, irrespective of their spins, and that doesn't need any special exclusion principle. In the standard model of electrons, they are ascribed a property called spin. Standard model practitioners have no idea what it is. However, they insist that it does not have any classical analogy and completely reject the concept of spin being angular momentum. In the Bohr model, it was postulated that electrons traveled in pairs to match observation. No physical reason was given for their preference for pairs. Furthermore, those pairs of electrons had opposite spins to satisfy Pauli's exclusion principle. Now we come to the most important roles of electrons around nuclei and atoms. The first is to neutralize the proton's positive charge. The second is to bond with other atoms to form structures. So just how and why do electrons make atoms bond together in the myriad ways we observe around us? In this rotating photon model, electrons in atoms form molecules, crystals, and other structures due to their need to pair so they can exchange photons to change the orientation of their angular momentum and through that change their direction of travel. The Bohr model postulates that the necessity of electrons to form pairs is the reason for chemical bonding. Yes, it is a postulate, and yes, it is true and does work. But it gives no idea of why or just how strong that bonding is in electron pairing. That brings us to one significant difference between quantum mechanics as it is applied and this rotating photon model. Quantum mechanics treats spin as a peculiarly quantum mechanical property with no mechanical analogy. That was shorthand for, we don't have a clue what spin is, we just know that everything has it. In this rotating photon model, an electron spin is the angular momentum of the photon rotating twice within its wavelength. While it may not sound like much, it is the entire mass of the electron rotating at the speed of light. It has the second largest angular momentum to mass ratio of everything in the universe. Only an electron neutrino has larger angular momentum to mass ratio. It is reasonably common knowledge that it is difficult to get a gyroscope, such as a bicycle wheel rotating at a few hundred revolutions per minute, to change its direction of travel by brute force. A good experimentalist might be able to get a bicycle rim with tire rotating at 50 revolutions per second. That would be a very strong gyroscope, particularly if a tire was filled with water. It would be difficult to get it to change direction by arm muscle only. Get a similar gyroscope and put the two axes of rotations in good physical contact with each other, the pair can be easily turned any which way, whatever. Now imagine something with an angular velocity to mass ratio billions of times that. That has one very powerful effect on the behavior of the electron. It dominates them. That is why electrons must pair wherever possible. It is all right for quantum mechanics practitioners to say that electron pairing is the basis of atomic bonding, but it gives no indication just how strong is that necessity to bond. So perhaps the next time when you venture into a forest in the wilderness and you see trees growing up hundreds of feet tall, reflect for a moment that the molecules make their way all to the top of the tree because of the angular momentum of their electrons. Yes, electrons are responsible for almost all effects, gravity and nuclear excluded. After its charge, an electron's angular momentum to mass ratio is its property that has the most influence on its behavior. It is that ratio that makes atoms' binding properties so strong. Electrons have to bind at least in pairs or multiples of pairs to be able to change their direction and move around a nucleus. Quantum mechanics was developed because the electron as a particle had so many apparently contradictory properties that it could not be understood. It was easier to treat them as waves because waves can be transformed and manipulated to get answers that match observation. Properties can be added mathematically as required to match observation. Theoretically, waves extend over great distances, so it should not be hard to get the right answer. There are a couple of frequently made comments involving quantum mechanics. Quantum calculations are carried out in an imaginary world. Every so often, the mathematics is brought into the real world so we can check them out against reality. And the other one is, when you think you know what's going on in quantum mechanics, you're wrong. All the physics I have presented has been calculated in the real world. They describe what is going on and why. It is your choice as to which you prefer to believe. It is not only electrons that have been treated in that way. The apparent complexities of the minuscule femto to nano world of subatomic particles has been introduced by people trying to use mathematics to solve problems. The same wave techniques have been applied to protons, neutrons, and neutrinos. It leaves theoreticians with absolutely no idea what are neutrinos. There are very few photon specialists who would agree on the nature of photons. The standard model describes them as point particles with properties attached. Theoretical progress in nuclear physics has been slow as endless variations of quantum electrodynamics have stalled its progress. Particle physicists are chasing their trails, trying to get larger and larger machines to find an order that has eluded them for decades. Theoreticians are going nowhere in their efforts to unite Einstein's relativity and gravity theories with their quantum field theories. In my opinion, the biggest cause of quantum mechanical complexities is because its practitioners don't understand that spin is actually angular momentum, and that conservation of angular momentum is the driving force behind the structure and properties of all particles. Protons, electrons, neutrons, and neutrinos are particles. It's time to treat them as such. Planck's constant and quantization are an essential part of particles. In the few brief presentations, I have shown that treating them as particles has explained the properties that were previously considered only possible under quantum mechanics. It is suggested that treating particles as particles under this rotating photon model will significantly improve the understanding of properties in the femto to nano worlds. Nothing I have said earlier is meant to cast any aspersion on the work of pioneers such as Bohr, Schrödinger, Dirac, and numerous others. They worked with limited knowledge available about 100 years ago. Their equations have worked out quite well. Most of those following on have not been able to make similar progress. This is my last presentation on the small end of the universe. From atoms to galaxies, galactic rotation excluded, most of modern science has done a very good job, far better than any other group. However, it still has many unknowns based around aspects of gravity that need to be explained. As this list of my future presentations show, I will be discussing gravity and relativity in terms of particles. There I will show how photon properties change Newton's gravity into Einstein's gravity and will extend their calculations to a new level of understanding. Here is a list of some of the topics that I can still present for those who are interested. Before I do, I would like to acknowledge the previous generation of physicists who laid the foundations for all the wonderful benefits of our modern world. In my opinion, men like Newton, who laid the foundations for the mechanical world, Faraday, who showed how to generate electricity mechanically. Maxwell, who laid the foundations of electricity and magnetism, made the greatest contribution to modern world progress. Einstein's E = mc squared laid the foundations for the nuclear age. Shockley, Bardeen, and Bretain's development of the transistor laid the foundations for the electronic age and the digital revolution. Thank you.